Hi, everybody. So what I wanted to do today was talk a little bit about deep forest and airborne biodiversity monitoring. But I think what I start with is a sense of a general purpose here. Like, why are we doing this? Like, what is it that we hope to achieve? And one of the things that's happened in the community in the last 10 years is that there has been an explosion of passive monitoring techniques for biodiversity monitoring, for ecological monitoring, from cameras, from camera traps, from airborne drones, from sensors, from undersea vehicles. And so I think as a community, we're starting to move into the spaces that we have so much data from passive monitoring sources, but we lack the ability to turn that data into ecological information. And so at its core, the thing that my lab cares about is turning sensor data into ecological information. Because the innovations we've seen in machine learning in the last 10 years truly are spectacular, frankly. And the change in what we can expect as ecologists and our responsibility as ecologists, I think, has changed tremendously. And I'm happy to talk about that more later. But I'll give the analogy, which is that I had the chair of my thesis committee many years ago, was a Bayesian ecologist. And she would say that, in the 1970s, if you needed a statistical model, you might go into a stats department and go get a Bayesian ecologist or a Bayesian statistician, and they would collaborate with you on some model building, right? And at some point during the last 30 years, the kind of quantitative modeling that is now pretty commonplace in wildlife ecology became the responsibility of ecologists. It became something we teach in grad school. It became something that we expect grad students to understand and something faculty to understand. I believe the same thing is happening with machine learning, and that 10 years ago, you would go and get a computer scientist to help you think about this stuff. The stack, frankly, now is mature enough, and we understand more or less what's happening in the biodiversity space, that I think the transition is happening as well. And so I'm interested in talking to faculty about how we teach this. I'm interested in talking to deans about how we fund this. I think there is a genuine paradigm shift in what we expect as ecologists in this space. And deep forest is part of that. I'll give a very brief history here because it does actually matter, which is, and it speaks to the thing I just said. Deep forest, I'll share here. Desktop one. Okay. So deep forests came about in a funny way, and it actually does matter. So I wrote this paper a few years ago now on tree detection, where we were trying to develop a model for NEON, the National Ecological Observatory Network, for tree crown prediction. And we wanted to draw a box around every tree. We developed a model. It was a nice model. It was not revolutionary in terms of its technical things. We used some weak labeling and some really interesting things there. I encourage you to read the paper. It was a cool model. What happened at the time was that we wanted to make a reproducible workflow for that paper. And so we built a small Python package that you could install. We never intended for the model we created to be used outside of NEON. We didn't intend it for it to be used by drones. We didn't intend it to be used for satellites. We didn't intend it to have a global reach. But what happened is that within the first 6 months, we had 15,000 downloads. And within the first year, we had hundreds of users asking us to try to diversify the model from neon data to their local drone or their satellite or whatever happened. It became so obvious that there was a tremendous need within the community. And so sometimes you'll see things within Deep Forest that are either like tree related, even the name itself, or like implicit to neon data. And I want to say that one of the things we're working on right now is Deep Forest 2.0 is trying to move us towards a much more general tool. It was never our intention to build a general object detection tool for biodiversity monitoring. And you will see that as ghosts in the code some places, and we're working with them that. It explicitly is because users have just taken this to a place that we have never anticipated, that frankly, we've had to respond to users' needs. Deep Forest is at 200,000 downloads now. It's the default tree detection package within ArcGIS. If you go to ArcGIS and say tree detection, you're actually just running Deep Forest under the hood. There's all sorts of things that are happening now that frankly outpaced our development ability. And so one of the things I want to stress at the top before I show any code is absolutely everything you contribute, it will be used and valued. That's data, that's questions, that's issues. Please go to the GitHub repo and anything you don't like, make an issue for. Hey, I don't like the name of this function. Hey, this is hard. I want this. I would love nothing more than to end this session with 200 new issues on the GitHub repo about things you want or things you don't understand or things that need to be better. That is the fundamental thing that would help us move forward, as well as understanding the pieces of data that the community has that we can make sense of within the licensing that's reasonable. And so I wanted to say that right at the top. The next thing I want to say is that because of that product, because of that history of starting with tree detection and again making neon models, but not necessarily realizing that they were going to be used in other circumstances, we've had to go back now and make a new data set and benchmark and a new model for tree detection at a global scale. We're calling it the Million Trees model. It's not quite released yet, so this is a front page, but you can't download this. We're looking for 1 million views of trees around the world. So that is point, polygon, field-related stems. So if anyone in the audience has data that is airborne data with annotations of trees anywhere in the world, we're looking to wrap that into a giant benchmark. We have 61 submissions so far. I think it's 600,000 trees. We've talked to Forest Geo, we've talked to Neon, we've talked to the large organizations, Smithsonian, who I'm meeting with today. And so if anyone is interested in joining the Million Trees Project, we're all going to publish a paper together and then try to wrap this into a benchmark to train a new deep forest backbone model for trees. So I'll just say that at the top. I won't say anything more about Million Trees, but it's there and we're starting to work towards that. And we're hoping to release maybe the beginning of the summer. But that's enough about that. So the next thing that happened was that we applied all of this data, all this modeling to NEON data. Many of you will be familiar with the National Ecological Observatory Network, NEON. And the goal from the NEON project was to try to predict the location and species, which is not included in this particular model, of individual trees. Give that a second to render. There we go. And so you can go to visualize.atrees.org and you can look at a bunch of NEON sites and you will see tens of millions of predicted trees. This is what we are trying to do at the broad scale, make this model available. You can click on them. They have species scores and that kind of stuff. If you have interest in NEON data itself, that's not what I'll be talking about today. You're welcome to reach out with us and to talk about NEON and tree detection and tree work within NEON and how we use this data for other places as well. Everything you see today is open source. We are aggressively collaborative and open source. We're committed to it. And so I will do my best to make anything available to anyone that we can. And so my hope today is to engage people both in the tool we're building as well as the kind of data products that I think are going to be really important moving forward because there's all sorts of cool stuff happening. Okay, that is enough show and tell. Let's start with DeepForest. Cool. So DeepForest starts as a Python package. The best way to get started is to install it using Conda. I will talk a little bit today about what I see as best practices within airborne machine learning. And so some of that relates to DeepForest itself and some of it relates to the environment. Please use Conda. Please do not install into your local environment. It's always a mistake. Make a Conda environment, make a clean Conda environment, and then pip install DeepForest. So the way it works is download Conda, say Conda create new. You'll find thousands of instructions on the internet how to do that. And then create a new environment and say pip install DeepForest. For those of you not familiar with Python, this is the dominant way in which packages are distributed. This is the most common way, and it will wrap everything and install. If you have any installation issues, please create an issue on our GitHub repo, and we'll be happy to help you install anything that you need. But this is aggressively tested every night. And so there is an automated testing suite. So there should be no problems with installs. And if there are, we get to them pretty quickly. So Conda install, you can do through DeepForest to specifically, or you can create your own Conda environment and pip install. That's what I typically do. And that usually works fine. So what is DeepForest in terms of the functionality, right? People usually arrive looking for a pre-built model. And so we've selected 3 things right now that we see lots of users wanting. If you have another need of a pre-built model, I am happy to talk to you about what kind of data there are out there and what kind of general use there are. People start from these pre-built models and then apply them to their own systems. So we have tree detection, bird detection, and then I would sort of general livestock detection. Those are the three categories of things that people generally want. Now, you're not necessarily limited to those taxa. We found out recently, that was pretty cool. I could show it somewhere, that bird detection also generalizes to manatees. We didn't know that. Someone grabbed it and was like, I think my thing looks well. And they cross-predicted into different spaces. And so one of the things that's happening right now is that you can fine-tune the backbone model, which I'll explain in a second, to your own taxa and system. And you'll find that because the tree detection model has seen hundreds of millions of trees through synthetic training, and because the bird model has seen hundreds of thousands of annotations, you'll find that there are ways in which it generalizes that are unexpected. The pre-built models are awesome, but frankly, we never think of them as what we call a zero-shot tool. In machine learning, we think of zero shot as, hey, I have a completely brand new data set, no annotations, no local data, and we're going to apply our model into that space. That is not where machine learning for biodiversity is. I would love for us 10 years from now to have a supreme general intelligence wherein we can apply it to zero shot situations across sensors, across resolutions, across backgrounds, across taxa. But the world is just too diverse right now for us to be able to do that. And so you should always arrive at DeepForest with the expectation to fine tune the model, bring your own annotations, and improve it. But we have shown again and again and again, starting from a pre-built model is massively important, reduces the amount of time you need, and also, frankly, sort of canalizes the learning workflow such that you actually get a result that you can use much, much more quickly. And so pre-built models are awesome for filtering data. They're awesome for coming up with labeled data and training, but they are not application ready in that kind of way. And we never think of them to be. If you see anyone claiming in any space in biodiversity monitoring in any taxa that they have a supreme general and tool that can generalize to zero shot tools across, I don't believe it. I haven't seen it. I'm the main reviewer for deep learning tools for biodiversity monitoring. We have not reached that point yet, and there are many obstacles that I'm interested in talking to computer scientists about that are really interesting, but that's not where we are right now, and we should say that really explicitly. I'm going to show a couple pieces of code right now and sort of walk you through the general use case. This just happened to be what I was thinking about when I started writing this a few days ago, and I'll kind of show the general pieces here. I don't really know whether I should take questions or kind of roll with it. Moderators, kind of, should I just keep going here? Like, I
Yeah.
see like things popping up.
Yep. I would keep going.
Cool.
Yep.
Awesome. So here on the Statistical Methods Seminar Series repo, you'll see this IPython notebook. It takes a couple times to load. I'm not quite sure why, maybe because this repo is a little large. So you got to refresh it a little bit. But I refreshed and it loaded. And so I'll be working within VS Code, but everything you'll see has already been executed here. Some of the stuff takes a little long, so I'll like toggle back and forth, if that makes sense. This is the first place that I want to talk a little bit about the machine learning stack for ecology and what it is that we use and how we use it. If you're not using VS Code or Cursor, don't do that. Stop whatever you're doing. Use VS Code or Cursor. We need to get in line with where industry is, with other open source places. And if you're not using Copilot and other types of generative code assist, you need to, and you need to now. The ability of Copilot to generate new pieces of code write me a Python script to rename all the files in my directory. The ability to write Copilot and it generate code, of course, it is not the kinds of things you should execute immediately, but it is so important to be able to code at the speed and the organization that it really is a transformative thing. For those of you who teach programming for ecologists, I cannot recommend enough starting to work with Copilot. It's an extension in VS Code. They've made a free version, but there's also a student version, which is extremely inexpensive. Might even be free at this point. And I cannot stress enough how impressive Copilot is and the ability to work with it. That being said, do not just trust it and execute code. You will find that it doesn't work, but that just because something doesn't work doesn't mean it's not valuable. I am a huge convert here, and I think that it's a game changer in terms of teaching ecologists code, especially for those of you who are familiar with R but not Python. Writing R code into Copilot and asking it to switch into Python is incredibly accurate, and frankly, something I do constantly. Um, so that's the first thing I will say is that use VS Code, use Copilot or Cursor, which is extremely similar, and you'll be happy for it. The second is that everything you'll see is on GitHub. I think the community has mostly moved into GitHub, and I don't need to extol its virtues there. So let's get into DeepForest. One of the things I've done is created some sample data here that you can download just from this Dropbox URL. I don't think if everyone does it at once, it'd be fine, but you'll be able to pull in. It's maybe a half gig of data of imagery, for example, so that we can play with something. So the first thing most people do when they make DeepForest is they load the model. This is for those of you less familiar with Python. Models are instantiated like this. Instead of R in the library function, we use import statements. So we'll say from DeepForest import main. OS is sort of a major package for operating system, which we'll use later. And this is general object-oriented structure, wherein we'll have something called model, and we're going to load the DeepForest model for birds. We have many different models that are labeled there on our Hugging Face repo. You can look through them. And so this will instantiate the weights of our bird model into your system. It'll download them, it'll place them there. There's nothing else to do. There's no like downloading weights from our repo or anything like that. That's not how the modern system works. The first thing we want to do is go look at that data and make predictions. The general construction here is predict image. So let's say we have a bunch of images that we grab from that data directory. We're going to loop through them and say for each image, let's say the first 4 images, we're going to make predictions. I'm going to call those zero shot because we'll look at them later. And we're going to visualize them. So we're using 2 DeepForest functions here, the predict image function and the visualize plot results function. The only thing I don't like about that is that the default color is blue and this background is a little bit hard. I don't know if people can see them, but they are well detected there. Can I zoom a little bit? I don't want to mess with it too much. But if you can see, there are blue boxes here on each of them. And in fact, I should just run everything. Let's run everything. And I'm going to be able to change things like the thickness. That'll take a moment to run. And so each of these boxes delineates a bird detection. There are blue boxes on almost all of the birds. That one's missing a box. But that's a reasonable zero shot performance. I did say before we're not zero shot. We're not perfect zero shot. This just happens to be an example. This data, the model has never seen before. I didn't even possess this data until 2 weeks ago. This is from the Deepwater Horizon post-oil spill surveys. It's not something I have anything to do with. I didn't cherry pick this in any way or shape or form. I went to the internet, downloaded some data, and grabbed the first 4 images. So nothing you're seeing here is constructed to look good or not. Some things will look good, some things they don't. I was trying to be as organic about it as possible. And so I'm gonna let that run. You can do things like change the thickness here, I believe it's called. I think it's thickness, but and that will allow you to see the predictions a little better. I should have thought of that. But here you can see them a little better here. So here's a bunch of turns on sand. And so this is what DeepForest bird model will get you. It's a reasonable starting place. It's not perfect, right? We're missing that bird. We're missing that bird's a little bit poor. But you can see one of the things that's challenging about ecological object detection from airborne perspectives is because the objects are not of any finite size, because obviously the image acquisition system can be close or it can be far. Your objects could be big, they could be small. It's difficult to imagine a general zero-shot tool that can orient in these different spaces. And so this kinds of stuff, there are birds here, but they're very hard to see even within the imagery themselves. And so I'm looking at birds that do look like good detections all the way here. Those all look like birds, but then maybe here 1 or 2 of them aren't actually birds. But again, they're so small, it's actually difficult to see. And so one of the things I want to stress to users, I liked this example, was that machine learning is not magic. In fact, it's actually much simpler than most people make them out to be. So the rule of thumb is if you can't do it, the computer can't either. If you can do it, the computer can with enough data. So
there's not usually a situation wherein an annotator can't do something, but a model later can. That's pretty rare. And so one of the things I want to stress for airborne data is if you can't classify your species in your imagery because it's too hard to see, the model is not going to be able to do so either. There isn't another axis of information to teach the model. Similarly, you can only expect the model to have sets of context. So here, for example, we're looking at a bird colony, but now suddenly it's massively farther away, right? We went from terns that we can individually see to here, there's a bird colony in here. Each of these white dots are birds within some sort of colony, it looks like. And we've got a couple birds that are flying that are labeled, but this giant sand pit is just an error. And obviously all these birds are missed. And so this shows the range of imagery that you could show to deep forest models and that you need to improve. So this is usually the first step. It's really what people end up doing is that they grab a model, they apply it to the data, and they see how does it need to improve. I want to stress why this isn't so important. The average machine learning project in ecology, what happens is that you go out, you collect a bunch of imagery data. You then send it to a bunch of annotators. Sometimes we have undergrads, sometimes we have outside annotators, and they annotate a bunch of examples. And then you go and train the model. This is the wrong way to do it. What we want to do is instead of collect all the data, annotate all the data, develop the models, we must create iterative pipelines that do small bits at a time. Because what happens is that we over annotate pieces we think the model needs, and we under annotate pieces that we don't realize the model needs. We need that the model decide for ourselves by looking at explicit predictions about what you need to do. So don't go over the summer, collect all your data, pass it to a bunch of annotators, annotate everything, and then be like, in the fall, we're going to develop a model. That is we've seen it again and again and again, a surefire recipe for error. What we do is iteratively, the best case scenario, which is obviously difficult to do, would be to fly a drone that night, do a couple annotations, develop a model, have an automated system, make predictions. The next day, figure out what pieces of data your model needs to be better in a tight iterative loop. That obviously is overly optimistic about what we can attain, but that is where we should be going. Very tight loops of annotation, model development, data collection. That is the way we've seen projects be successful and not as these huge blocks. And I think that's probably applicable to other types of ecological information as well, in terms of the forecasting narrative we have here. What we use for annotation, I highly recommend Label Studio. There's a free version of it that works super well. It's pip install Label Studio, and then you can open it up on your own machine. You can also serve it as a server within the browser. Label Studio has a market, first round venture cap of like 25 million. Like they've done a really good job. They know what they're doing. We do not need specific annotation environments specific to biodiversity or any of this stuff. We should use what the rest of the industry uses because there's billions of dollars here at stake. And so the development space here, there's just no reason for us to bubble off something specific for ecology and then wonder why it doesn't work as well. We should use what the self-driving car people use because that's where the money is. And so Label Studio is a really nice tool. I think actually some of my annotators are here if you want to talk to them in chat. If anyone wants to yell at Briar, I think she was here. I saw her. And so if you want to ask about Label Studio and how annotators work with it, we have a team of lovely annotators who work super hard, who I value tremendously because every day I post data, they annotate it, we develop new models. We're working on a series of models all at the same time. And so having a tight connection to your annotators and valuing them in terms of being part of the scientific process is hugely valuable. Too often what we see is that we pass on annotations to just like a bunch of undergrads and then they'll annotate it and come back. That leads to poor annotation. It leads to extra effort. What we do is we hire people, we pay them reasonable wages, and we ask them every day to work and engage with model development as part of their responsibility. Even though my annotators know nothing about machine learning, they offer good suggestions all the time about how we develop models because they're the ones looking at the data. And so we don't create a wall between annotation and model development. We talk to them, I talk to them daily, and that's how we get good space. Label Studio is super cool. You can pre-annotate in this space. I encourage you to look at the label docs. So for example, you can apply a DeepForest model into Label Studio, upload it with those annotations, and then it can edit those existing annotations. So if this is some airborne imagery from the Everglades, and so this might be a pre-annotated image. So the model's already made a set of predictions. And now our annotator is going to go back through and correct them. This is massively faster than, for example, having a model where the image is just blank. This is why I highly suggest using pre-built models to start with, either ours or other people's, because you can imagine that let's say a model is 60% accurate. You'll have 60% of the birds in this image labeled, which is 60% less effort for the annotator to go find them. Even if you can't, for example, do species classification yet, you've just got bird, it's so much easier, for example, to know that at this particular colony, let's say we have the metadata, only great egrets occur. So I can grab a whole box. You can do this in Label Studio, grab this box and go whoop, and you can select everything in that. And now you can apply one label to all of those boxes all at once. So now suddenly you've labeled 80 birds as great egret because you know that that's what's there. And you've already had the birds pre-labeled. That goes from, hey, I can label this imagery in 15 seconds versus 10 minutes or 20 minutes. And when we're talking about tens of thousands of images, this stuff matters. I can show an example of Label Studio in a live feed if you want at the end of this, but I want to get to some more code. You can export data out of Label Studio in a number of formats. I like using the different sort of XML formats. The one I use is called Pascal VOC, BVOC, which is a very common one. But you can use CSV formats, and the DeepForest docs describe the different formats here. We have a general purpose function called readFile, which looks at your file ending and tries to figure out which parser to use. So there's no like guessing at which thing. So we can take in shape files. So if you have ArcGIS or QGIS and you load your imagery up and click on a bunch of trees or birds or whatever it is, you can upload that shape file and have the parser there. If there's other developers in the room, I cannot stress enough, a general purpose parser is a really nice tool, and stop asking users to like match your parser with the data they came from. Your functions should know and try to make reasonable assumptions about it. That has been a really important tool for DeepForest users, is that they got sick of trying to figure out which input parser to use. And now we just have one and it tries to guess. It is sometimes wrong, but mostly it's a very useful tool. So for example, this one's a CSV file wherein each row is a label and has a certain format, which is documented. And that will allow us to make predictions of different annotations. So these now are not predictions, but these are things that our annotator, I think this one was made by our annotator Ash, to look through and click on each individual bird. One really important thing for machine learning for biodiversity analysis that always is asked and is very unfortunately true is that you do need to implicitly label every single instance of your class in the image. Everyone's like, oh, can I like do some of them? What happens is if you train a model with some of them, it's implicitly learning background. And so every time it sees a bird, for example, or a tree that isn't labeled, but you should have been labeled, but you didn't want to, it's down weighting that potential box. And now you're going to get worse models. And so it's better to do images fully and fewer images than many images incompletely. And that is something we learned and people constantly ask, because especially with trees, you'll get these images of 5,000, 10,000 trees, and you're like, I don't want to do all of this. If there are computer scientists in the room, this kind of instance segmentation is quite interesting. And there are some nice loss functions to handle this. We have not built them into DeepForest. And if anyone's looking for a project, incomplete loss functions is something we would be interested in implementing. I've done it for projects, but not into DeepForest because we don't have a general purpose solution with the class imbalance for the kind of object detection tools we use. I don't know what kind of audience I'm talking to here. So if there are computer scientists here, that is an interesting problem that we would love to keep working on. So these are annotations now, not predictions, of individual birds in those imagery. And we're going to feed these annotations into the pre-built model and improve them. The next thing that's going to happen is after we load the data, the annotations, we want to create train test splits. It's incredibly important that you make logical train test splits. Ironically, I'm not doing it in this case because there is no logic to this random data set I created, but hear me out. It is incredibly important that you have train tests that represent the kinds of prediction you're going to make. One of the most common reasons to get papers rejected in this space is that your train test splits are just done randomly. The vast majority of papers you'll see just have a bunch of data and they take 90% of it put over there for train and 10% of it put over there for test. That is a terrible strategy and invariably leads to overly rosy performance predictions. And one of the reasons that downstream users have become exhausted with the purported scores for many ecological models is that they are randomly split. And so they look much better than they actually are. If you're going to make predictions through time, you need to split your data through time. If you're going to make predictions across space, you need to split your data across space. And so, for example, in the Everglades, we have a bunch of bird colonies, and we might label one colony, and now we're going to predict another colony. We need training data that holds out an entire geographic area. If we're going to predict through time, you need to take data from 1 year and to predict into the next year. And you should be explicit about that in your papers and in your analysis, because it'll actually show you what happens. What we find is that people often randomly split. They find that their performance is pretty good, but the model is learning something implicitly about that structure. And so we see very poor rigor in train test splits. And I would say that is like one of the dominant problems in the space. And I assume is actually problematic in the forecasting space as well, is this desire to train. Some of it is cultural, and we need to get through that both as reviewers and scientists. We expect nice numbers. We want good numbers. We feel nice about high value scores, right? It's very pleasing to have an 80% accurate model. If you have a problem in airborne machine learning that is worth studying and you are getting more than 90% accuracy, you've done something wrong. Like this, I don't believe it because it's just too difficult. Either the problem is constrained somehow or your trained test is not rigorous enough. In general, we tell people that your first pass in a model should be somewhere between 65 and 75% accurate. That is usually like, that sounds about right. If you have a pass in a model and it's 98% accurate, either you're leaking trained test somehow, or you haven't set up your problem in a way that's rigorous enough that someone else is going to care about. Of course, you can create toy problems, which you score well in, but in general, model scores should be much lower than they are. And if you look through the literature, you see an epidemic of, in tree detection, for example, an epidemic of 95% accuracy. That's one of the ways I know immediately that the paper was not well done. If I see 65% accuracy, I start to get interested. And so it's a very perverse thing that some of you who I might have reviewed your papers might have seen. Okay, so we're going to take annotations. We have a pre-built model. We've made predictions. We've used those predictions to help structure annotation. We're going to annotate the model. We're going to annotate examples in train. In test, we don't want to use the pre-built model at all, right? Because we don't want to pollute that. So we separate what's train and what's test, and we annotate them differently. Another reason why it's super important to have logical train test splits is we don't annotate everything and then split them to train test, because I'm going to treat the way I annotate train differently than the way I annotate test. For train, I'm happy to use the pre-built model to make existing predictions. For test, I can't do that because now I'm biasing towards the pre-built model. And so literally in Label Studio, I have for my annotators a project for train and a project for test, and I treat them differently. That's a very important step. All right, let's fine tune an example. The way DeepForest works is that we use this backbone model. Again, I open up. We have a config file, which is documented on the docs, and basically think of it as a Python dictionary that is a bunch of options about where the data lives and how often I want to look at it. I don't know how much detail to go into in terms of machine learning sort of basics here, but an epoch or an epoch, depends on who people want to say, is one view of your data. So think of it as a full pass through whatever training data you have. This represents usually like a pretty safe start, which is that I want to look at my data 20 times, my training data 20 times. Every other time I'm going to evaluate it, and I'm going to start at a pretty low learning rate. The two most important parameters in our system for fine tuning, or at least retraining in this case, we're not freezing any layers, is the number of times you look at your data, the number of epochs, and how much we learn on each step, which is our learning rates. Those two hyperparameters are really important. They can have huge effect and they need to be explored. There is no general solution that we have been aware of about how the model will respond to different learning rates. Again, if there are CS students here that want to think about learning rate optimizations, there's some really cool stuff here. But we generally have very low learning rates because the models are pretty good. And so we want small changes, not massive changes. The smaller the number, the smaller the learning, and the less that the backbone will change per epoch. So we say longer and slow versus faster and short tends to be what we want. I want to talk briefly about Comet because it's a really nice tool. And again, it's something that people should be able to use, and I highly recommend. I haven't brought it up, so let's do it. Comet ML. Comet is another one of these startups that has a free version for academics that is incredibly powerful. Am I logged in here? I am logged in here. Okay. So what do I want to show? I'm going to show this. Comet is what just happened there? Comet is a machine learning dashboard wherein each of your runs is submitted to the dashboard, and you can see the experiments, how long it run, what the evaluation score was, how it performed on all these different measures, and allows you to look at the different experiments you do over time. Let's look at one of the tree experiments. This is incredibly important because one of the places we see failure points within machine learning for biodiversity monitoring is in tracking your experiments. PyTorch through DeepForest allows you to connect Comet in one line of code. It's incredibly powerful and really, really useful. So let's grab, and this is the real key thing. I can compare experiments, and it will show me which hyperparameters were different between those experiments. So for example, here I have two different data sets in this particular random example I'm using. I can compare the code, the performance of those two models over time. I haven't coded any of this. Comet does all this for you. It's super impressive. Again, we need to connect to industry and what industry standards are rather than having ecology specific tools. This isn't something specific for ecology. It's a general tool. Again, they have a first round venture cap of like 55 million. They know what they're doing. We don't need anything different. It has system metrics for GPU usage. You can upload images within it, graphics for different comparison between different runs. You can look at those metrics and hyperparameters. Your model definition is saved there. And again, all of this happens automatically through attaching your logger to DeepForest. So I highly recommend Comet. I think it's an essential tool to use for machine learning, regardless of what type of modality you're using. I really, really think it's awesome. And so the killer thing here, and the reason GitHub is so important, is if I don't know if this particular example is going to work. Yeah. But if you make every experiment you run on machine learning in GitHub a commit, every time you may change one thing and then you make an experiment, Comet will log that. And the virtue there is then you can compare those experiments explicitly on GitHub through Comet. So this tells me that these two experiments differ in this code, and I know explicitly now how my metrics relate to my performance and how that relates to my code. Very often what we see is people have these Excel sheets and they're like typing a bunch of stuff, and then they try to like recommit and figure out what everything happens is. What we often tell people is your best collaborator is you 6 months from now, and you don't respond to emails, right? You have to have a system that actually tracks everything for you. And there's no like, I'm not writing anything down, right? I don't like go to another Google Doc and be like, that one was 0.97. That doesn't work. What you need is a system that actually is mature enough to understand how this changes over time. And so Comet is a way of doing that. You can explore GitHub here. And so every experiment you run is a code. It does lead to very heavy repos, so you have to be careful about that. That's the reason that this repo has 4,000 commits, because I made 4,000 experiments. And so each commit is an experiment. And that allows me explicitly to go back at any point in time to any result I want, because of course I can just git commit and check out that particular experiment. And so I never get worried about trying something new because I always know I can go back. And Comet plus GitHub allows me to do that. And it's incredibly useful and freeing in terms of the creativity of the machine learning modeling part. Okay, let's go back to VS Code. So these are some of the hyperparameters I'm going to use to fit the model. Here's that Comet logger. It's using my API key that's in my config file. It's going to tell me that it's starting to run. Here, for example, just like following through on that, it's explicitly telling me the Comet page that was for this run. So now I have an explicit connection to that Comet run. And so you'll see, for example, in the IPython notebook, like, hey, there's no loss curves or anything. Where are my loss curves or anything like that, right? Comet's logging all that for you. And so you don't have to worry about visualizing any of that. So here on the x-axis is epoch, right? We said 20 epochs. And here's an evaluation metric, for example, box recall. It's the proportion of ground truth that we get. And we see over time, we're improving in terms of our box recall. We started out about 37% accurate, and we moved to about 50% accurate through these 20 epochs. I bet if I kept training, it would go further. And so this is the way in which machine learning development works, is that you make a change with your data. You then look at those graphs and figure out what do I need to do differently and continue forward. And so here's my loss curves, for example. I won't go too deep into this for those of you who are less familiar with machine learning loss functions, but here we have a classification loss. So that's basically the background and the foreground here because we only have one class, which is bird. And this is the overall loss that's dropping. And so we can look at these loss curves, for example, and as you grab some intuition, you'll find that like I should run this longer, right? We want this asymptote like much cleaner for much longer. And so this is a too short run. That's the kind of thing that you'll learn from these curves. So we can fine tune this model, and we can then make predictions with this model to see how it performs, right? So we have held out data, gives you a bunch of responses. Now we're going to go predict that same data from before and see how we performed better or worse. And we see a couple bits of our prediction here, right? We've added some boxes that I'm not in love with, and hopefully that'll be a little better as we run out. But in general, it looks better, right? We went from a third accurate to half accurate. As I look here, I'm not convinced these are all birds. 1, 2, 3, the boxes in the middle. It's a little hard probably on Zoom for you to see, but as you go to the GitHub repo, you can zoom in. And so we have some a little bit over predictions here. So it leads us to the most natural question, which is how many annotations we need, which is the vast majority of people ask me this question as if we have some sort of wand and knowing how many annotations you need. The way to actually do this is to have this iterative tight cycle where you're doing model development over time. And this is the point of doing that, is that you can actually see the rarefaction of your annotation performance. If you don't do that, if you just like collect all your data and then annotate all your data, you have no idea whether you did enough or too little. You have no sense of it at all. And what you do is you end up over annotating the common examples because they're easy to do and under annotating the hard examples. And the only way to know what's easy and what's hard is asking the model. That's the only way forward. And so by explicitly incorporating either daily or weekly annotation structures, we can start looking at rarefaction, which makes total sense. Okay, so now we're going to take that entire data set. We'll start with 0% of the data set, that training data, and now 5%, 10%, 50%, 90%, right? And we want to look at the performance differences of that annotation over time and what the shape of that curve looks like. So for example, what this looks like here is the proportion of our training set. So this was, I think, we just did this last week, so it was not much. Maybe we did like 5,000 annotations, which doesn't, again, might sound like a lot, but if you have them pre-predicted into Label Studio, that's, I don't know, I think it probably was 2.5 days of effort for our annotators. And while they are wonderful annotators, they're not like superhuman in any way. So it's not that much effort. And so we can look at a portion of the data set. So this was the zero-shot performance, and this is how we improve over time. When I look at this curve, we still need to annotate more, right? We want to flatten this thing out to basically say that no new annotations are useful within this space. I'm looking at the precision, which is the proportion of predictions which are true, versus the recall, which is the proportion of predictions that are true that we correctly predict. Having both precision and recall is incredibly important. One of the other things that we see in review quite a bit is an over focus on recall. This gets very silly very quickly, and I'll tell a slight tangent. We ran a competition for tree detection a few years ago. So we had a bunch of ground truth, right? So there were a bunch of trees on the image. Let's say there was 3 trees, and they had boxes around them. 1, 2, 3 boxes. And we were just measuring leaderboard performance on recall. So a very clever grad student came by and put boxes in every single pixel in the image and correctly got 100% recall because every box did fall within a ground truth prediction. We were not measuring precision. And so what we did, they just flattened the image with 10,000 boxes and said, hey, I got 100% recall, put me at the top of the leaderboard, which is true. And so we did. But that is exactly the kinds of things you will see. That is obviously a gamification of the whole thing. But if you look carefully within the literature, you will see this happening constantly, wherein there's an overemphasis on recall and an underemphasis on precision. And so because of that, you will see models which just toss predictions out into the wind. And it's like, hey, I got a lot of things right. It doesn't ask how often you got things right. But what we do when we prioritize recall, and we'd even do it implicitly. Sometimes the precision metric's there. You'll see it in the table. It'll be like recall this level, recall this level, recall this level. And like at the very bottom, like precision is like 0.05. People will hide their precision metrics at the bottom and their recall metrics at the top. And so F1 scores are really important, but frankly, explicitly splitting out recall and precision, I think are really valuable. And it depends on the kind of ecology you're doing. For wildlife monitoring, we often care about finding the things, and we're okay with false positives. So sometimes down-weighting precision is important, but it depends on your downstream application and things that we care about. I just have a few minutes left, so I want to show a couple other pieces of the DeepForest package and like what are the utilities we see for common use cases. Modern GPUs can only handle so much memory, and so one of the things that we find is that you often are splitting large orthomosaic tiles into pieces. So you might go out with a drone and you collect a bunch of images, for example, of a giant bird colony. Let's say you have 10,000 images, and then you overlay them into some 3D model or 2D panorama. But of course, that image is too large to put into a modern GPU. You can't have a 4 or 5, 10 gig image file. And so what we do is cut them into pieces. And so we have a nice utility for this called split raster that will cut your image into pieces and then make predictions on each of them. That's super helpful. So for example, here, I had some giant image that was, I think it was like 400 megs. This was passed to me by Audubon or they think the University of Texas. And the image gets cut into pieces. And so we can look at each of those crops. The other virtue of this is that now we've made the targets of interest much larger. And so it's much easier to predict. So before I was showing you the predict image function, that leads us to the predict tile function, which is the same format in DeepForest. Instead of predict underscore image, it's predict underscore tile. And because of that, what's going to happen is it's going to cut them into images, predict each image, and then remosaic them together. Where it joins up, it's going to overlay them and perform something called non-max suppression, which basically is trying to figure out which box to maintain for overlapping boxes. This is, I would say most people come to DeepForest for predict tile and not predict image, because in geospatial data, we tend to have very large data. And so predict image is nice, but most people use predict tile because it tends to be this thing. There is an interesting caveat here. I show predict tile right here. Hold on, I'll go. Oh, I didn't upload it. One of the things that you'll see in predict tile is there is a patch size argument. Same thing in split raster. I didn't show an example here. Is this patch size? One of the challenges we do face is patch size does matter. So if you have the same image and you cut it into tiny pieces versus the same image into a few large pieces, you will get a different result. And there isn't yet a way knowing about what the idealized patch size is. Again, if there's a CS student in here interested in a nice master's project, optimizing dynamic patch size for unknown objects based on the model weights would be really cool. And we've worked in that space a little bit. But basically, you have to explore different patch sizes to make sense of it. Our general expectation is that as the resolution of the imagery increases, your patch size should increase as well. And I think that makes sense. So if you have 1 centimeter drone data, you want a big patch. If you've got 60 centimeter satellite data, you want a smaller patch. And it has to do a little bit with the focal view. So for those of you who are thinking you could just multiply the resolution by the focal view to get the same patch size of like, oh, it should just always be 40 meters. And if my resolution is different, I'll just change it. That doesn't work at all, which is the most logical, reasonable thing. And we've shown that to be the worst idea. I don't have time to explain to you why, but it is not just maintaining focal view. There's some special sauce in choosing patch sizes that is genuinely difficult. And for the larger narrative here, it has to do with how to generalize into new resolutions. So at the top, Jody was talking about predicting into new spaces. And so this is similar thought, which is predicting to new resolutions. So you have different frequencies of data and the information is different. And it's not as simple as maintaining focal view and multiplying by the resolution, which some people thought would be a good idea. I want to stop pretty much there and talk about one last piece. I'll show one more utility and then just to take a few questions because I only have sort of 15 minutes left. Getting data out of DeepForest, most people want them in shape files. You want them usually within the geospatial structure. So one of the things that's important to understand is that your model has no idea about longitude and latitude and projected coordinates, right? So when you bring things into DeepForest, all the annotations are made relative to the top left corner. So you'll see them in sort of Cartesian coordinates, if you will. It's like X is 37 and Y is 45. But of course, that might occur somewhere on the Earth's surface, and you want to maintain that information. If you want to project back out, oh, here's the projectile function that I was talking about before. If you want to project that back out, we have the image to geocoordinates function, which allows you to take in an orthomosaic that might have some projection information, for example, through ArcGIS or through some structure through motion that you might be familiar with. You would take in that data, make a prediction on it, and then retransform that back into the coordinate system you came from and export it as a shapefile. And so now you can look at it in ArcGIS or any other geospatial mapping tool. That's super important because you want to be able to overlay them through time, for example, or on the Earth's surface. And so you need to convert back from pixel coordinates, where this is within the image, versus geospatial coordinates, where this is on the Earth's surface. I will say, for those of you who are like yelling at your computers right now, for extremely large tiles, right, we can't handle the curvature of the Earth. So for extremely large tiles, there will be a small shift. We found that to be very rare, but for satellite imagery, at the edges of the tiles, there is a small fisheye effect. And we can talk about, for those of you who are interested in studying that, but right, the Earth is a sphere and not a flat surface. And so there isn't a problem there that we can talk about. And so with that, I just want to reiterate that what we're doing for DeepForest is trying to develop a general object detection tool. If you have interest in building a pre-built model and contributing to us, if you have data that you think the community should need, please post it to Zenodo or lila.science, which is an object detection place that Dan Morris runs at Google. And so we would love to talk about how we can help you and build general tools. We're not a consulting shop, and so I can't run things for individual projects. But if you have something where you can articulate that you think hundreds of people are going to need this, then yes, I would love to talk to you and think about how I can help you and try to make this something that ecologists own for themselves, because I think we can do it. And you can see, we've built just a few, there's only 80 lines of code in this entire notebook. And we've gone from a nothing to a pre-built model to a fine-tuned model to exporting it out. And that was DeepForest in an hour. I can't believe I talked that fast. Thanks, everybody.
Yeah, thanks so much, Ben. That was really fantastic. I think I can speak for everyone and say that there's been a ton of resources you shared and great overview in just that short hour. So we do have a few questions that I'll kind of read off in order of upvotes. Just for those of you that did post some questions on there related to links and resources, Jody did put those in the Zoom chat. So take a look at those for all those great resources that Ben mentioned.
Can I just add, I will also send them out in the follow-up email that'll go out next Monday too.
Perfect. So the first question we have is, can DeepForest be used to classify tree health?
Yeah, so one of the things that we've built in is something called the crop model. And if we go to the docs, we'll see it. Sorry, there's also a cat who's going to make herself completely known. It's very funny. Come on, Cricket. There she is, everyone. This is my cat Cricket, and she says that this is time that she gets snuggles. So if we go to the DeepForest docs, we'll see something called the crop model. So after you make a prediction for tree, right, you on each bounding box, you might be interested in classifying that bounding box. And so we, for example, have a live dead model for trees that we make available. And so you can use the crop model to predict whether this looks like a defoliated tree or a snag. And so we've just started working on the crop models, and we have a ton of them that are on Hugging Face, the model repo that people haven't used yet. If you're interested in the crop model thing, please create a discussion on the DeepForest repo, and I can walk you through it, or we can figure out how to best use it. But it's something we are actively supporting and is there. We have a tree health model. Health seems unreasonable. Does it have leaves during periods of time when you didn't think it should have leaves? Do you know what I mean? Like, trees lose their leaves for lots of reasons, so health feels a little scary, but defoliated seems reasonable. That's something we are actively going to support, and we do have models for.
Fantastic. That's great. I'm sure a lot of people would find that Very useful. So next question is, do you have any thoughts on training deep learning models within Esri ArcGIS Pro instead of with code directly? I believe Esri has a deep learning model for trees that is based on DeepForest.
Yeah, so this is one of those interesting questions, which is that like depending on your comfort level in Python or not, like you will have more control over what happens in Python itself. But of course, that is a limitation for many people. I would stress to you that you're going to be happier long term just spending the extra week trying to develop the knowledge about how the Python environment works. The resources online plus Copilot has really changed things. I mean, it used to be such a slog to develop a new language understanding, but I really feel like the barrier to entry is totally different. At the same time, ArcGIS has some fun stuff that is really important in the ecosystem for those who are feeling intimidated by the code or don't feel like the code is the right choice for them in terms of their time management. You will get those results. The challenge, of course, is you won't have a lot of insight into what's happening. You're going to press train and you hope it works. And so I guess what I would say is, hey, maybe the first week, go for ArcGIS, see if it works. Press train, label a bunch of stuff, press train, see if the thing works for you. And if it does, you're like, awesome, get out of there, right? Because we're all trying to learn something about the natural world and not become CS, people. I really want to stress this at a high level, more so than this individual question, which is that I think more and more this is going to be part of our responsibility. And so trying to figure out what works for you in terms of mastering this for your project. We want to reduce the intimidation and reduce this expectation that there's some level of expertise that ecologists can't attain. I feel I get a lot of students who are like, I'm not smart enough to learn this. I'm like, it's 17 lines of code. There's nothing here, right? And so like one of the things I want to stress is that we can do this. All of you are talented in your own study system, and we should reduce the intimidation and try to figure out what works for everyone. And so that's part of our mission. If that's ArcGIS and I think it's like you kind of like select a bunch of them and you say like retrain model, I highly recommend stopping there and it's done. If that doesn't work for you, then these are resources that I think are available to further your learning.
Great, great. So next question we have is kind of a lot of things here. So please describe the use of a pre-built deep forest tree when possible within Label Studio. What are the steps? What are the pitfalls? What are the best practices for including labelers? Is there a tutorial available? So I guess maybe what sort of resources would you suggest for this person to kind of get going with?
Yeah, so we have a blog post on Label Studio integration with DeepForest. The truth is Label Studio is moving so quickly that it's a little outdated and like we only wrote it like 2.5 months ago. One of the things that's challenging at the high level here is that the stack is moving quite quickly because of the investment in the space through industry. And so things get replaced quite fast. There's a whole new Docker containers for Label Studio. They're super beautiful. I'm happy to create a discussion on the DeepForest page and show slowly, because I already have written the blog post, how to get this into Label Studio and structure it. I have a different repo that's on our GitHub page called Airborne Field Guide, where I start to walk through this, that we're starting to invest some time in. We work with the Bureau of Ocean Energy Management on some offshore surveys. And through that project, we are doing quite a bit of Label Studio work. And so in terms of the actual physical parts of this, go to Label Studio, pip install it, and run it locally on your computer. It works super well. It's not a scientific tool, it's a commercial tool, and there's a free version. Best practices for including labelers. I'll reiterate what I said before. Treat them like scientists and not like computers. Often what we see is that there's this sort of arm's distance between the model developer and the annotator. First, I will say as a model developer, if you're sitting in the room, you're never too good to annotate your own data. You're never too important to annotate your own data because that's actually how you become intimate with it to understand it more clearly. And so one of the things we often see is that through a desire through efficiency, and because we're all massively overcommitted, as we all no doubt are, we try to offshore or off-put things that other people can do. What happens is if you are developing a model, you need to spend time with your data and own that. Of course, the scale of annotation might happen through others, but you need to really be intimate with your data. And so being part of that process and communicating with your annotators is super important. I talk to my annotators every day. I talk to them about what they're seeing, what works. I have a list of things, a little Slack thing, like, what should we do next? Should we do this or should we do that? Right? Treat them like scientists. Also try to use that
part of the workflow, not as an engineering step, but as a scientific step. What's the fastest way we could annotate our data? Let's make 1,000 random images and try to annotate those 1,000 images as fast as possible. Let's try it 3 different ways. Okay, now that we've done that, what's the best way for us, right? And try to treat that like science rather than, and with all the tools that we know how we are, with all the things we know how to do, try to treat that part like science instead of just like, over the summer, I had a bunch of undergrads look at our data, because the truth is no one like cross validates their undergrads, right? No one ever like goes back through and be like, I wonder how good my undergrads are. How many times do they call an elephant a warthog, right? I had someone once tell me that their undergrads were perfect. Every undergrad they had were per camera traps. They had 1 million camera trap images, not a single of them wrong. Unpaid undergrads over the summer didn't do a single thing wrong, right? There's just no way. And so instead of pushing that out and be like, that's their responsibility, trying to incorporate that. Now, of course, we're all very busy, so it's a difficult answer, but that's part of what it is. The last thing I'll say about annotation is that going slowly and understanding through explicit prediction where your model fails is super important, especially for species diversity and species classification. So I'll give you the example of the trees. It's natural to just like throw people out into the landscape and collect as much tree data as possible. Like go, oh, that's like one, right? You just like go and spray your data and try to get as much data as possible. But because of class imbalance, the ratio of the most common class, the number of examples you have from your most common class to your rarest class, every time you collect a piece of data on your most common class, but you're also interested in your rarest class, you make it harder for the model. And people need to understand this more explicitly, which is that randomly sampling the landscape and having really common trees, for example, every time you collected a data point on the most common tree, it makes it harder for the model to predict the rarest tree. The same thing is true with over annotating classes. We see this as a constant thing because ecologists want to get to the end. They want to get to the paper. They're like, instead of just like starting with bird, they're like, we're going to do white-winged scoter, black-winged scoter, white-winged scoter, black scoter, surf scoter, but we're also going to do both morphs of them, whether they're nesting or breeding, right? So they annotate all of the classes. And the way I try to tell my annotators about this is like, imagine you're in the grocery store and there's one item on the shelf. It's really easy to select that item. Now there's 2 items, you can choose between them. But now there's 30 items. You got to read each of them. You got to figure it out. And that's exactly what's happening with the model. As the model is forced to make more choices in this embedded space, it has a harder time making choices. And so if you want a model that works well at first, start with fewer classes, get it to work, and then cascade that down versus annotating all of the classes at once. Because what happens is you end up like grabbing the first bottle of salad dressing. You're like, this one's good. And then you like run out, right? That's exactly what happens with the model is it makes poor choices when it's faced with too many of them. And so it's not possible necessarily to do everything you want immediately. And we see this very commonly with different tree classifications and all this kind of stuff is that there's like 37 classes. They're nested in awesome ways. You have to go slowly.
I'm
Great.
looking at the time and I
Sorry, I
wonder,
talk too much. It's just my nature.
it's great. And we've got a lot of good questions, but I know you need to get off for another call.
Yeah, I can be a couple minutes late. Other thing I'll say is that the DeepForest repo we monitor really carefully. So please post discussions if you don't get your question answered here. I will answer them in the next couple of days.
Great, thanks.
Let me answer the one because it's a quick answer. Are there resources for implementing DeepForest in R? There's a DeepForest R importer. It's called DeepForest R. It runs through Reticulates. For some of you might be familiar, it's like the Python package. It's less maintained and paid attention to. I would love people, if there's anyone who wants to spend more time on it here. We don't spend a ton of time on the DeepForest R package. It exists, but is probably a little bit behind. Again, with the Copilot resources, I recommend Python, but if you want to get into R and you're stuck with it, let's do it. Like make a repo. Well, it's got its own docs and everything. It's just not something we spend a ton of time on, but we can do it. By tight cycle, what exactly meant? The time between model development and new annotations. Develop a model, make new predictions, make new annotations from those predictions, and making sure that you create an understanding about where your model's failing. The unfortunate thing about deep learning models is that they became metaphors for human thinking. That was how they were sold. They're like neural networks, which was just a marketing tool, frankly. It was not a it's not implicit to the knowledge. It's just something we call them, right? And so because of that, humans map their expectations onto neural networks. And or our expectations are like, that one's hard, that one's easy. And so you start to foist your own expectations because you're treating it like a person, because it's called a thing that's like a mind. And what happens is that we often are very, very, very wrong at understanding what's hard and what's easy for a model. The only way to understand what's hard and what's easy for a model is to ask it. And then you have to make predictions and to figure out what's working well. And so that's the reason that you have to do that, is because of the narrative here that it's like kind of like a person or an intelligence. And so your intelligence can be a replacement for that. The problem is that we're no good at that, and we're often wrong. We're always wrong. What about the crop model then? You only have to label parts of the object in the picture. The crop model occurs on the per box basis. So there's no detections. So basically what you do is you crop everything and you give a label to that image, which is really just a sub image of it. And so it's just, you make all the detections. So here's a bunch of trees. You pull out those detections, and now you're going to say, this one's alive, this one's dead. And so while you as an annotator might go through and do that within a landscape, and I understand what you mean by only a portion of them, from the model's perspective, it's fully annotated because it's just paying attention to that one crop versus another crop, not the whole object detection pathway. It's cascaded, if that word means the right thing to you. It's first detection, then classification as separate workflows, and not a one-stage model where it detects and classifies at the same time. And there it is. I cleared out the whole thing.
If you
Yeah.
refresh, I think there are a couple more.
Oh, come on now. Come on. Okay, wait, we do it. Boom. All right. Sorry, this is for those of you in the audience who knows me, this is how I always am. So some of you are laughing. I can see Ian's here. I can see a couple people who know me. So this is funny. I can't stop. Has DeepForest been used out of detection other than RGB? Boom. Okay, this is a good question. So we have an HSI model that does work for tree species. The challenge with hyperspectral, and this again is mapping that human intelligence on, is that the model has no implicit understanding of hyperspectral space or like nanometers or image lengths, right? It's just a set of arrays, NumPy arrays. So it just, if you have 369 bands versus 10 bands, it doesn't know that like band 12 is this part of the visual spectrum. And so predicting across different number of arrays is still really difficult. It's something we have a grant to write about, and we have some funding for, but not enough time to spend on it. And so the short answer is yes, we've tried it, but predicting across number of bands, so if you have 3-band versus 4-band data, is still hard, explicitly because of the reason I talked about before. The model it's not smart. It doesn't know that you're just adding another channel. It has a whole thing from scratch. And so I'm happy to talk in the discussion page about how to go about that. And you can use the data, but I would firmly call it non-standard. And again, somewhere we need to go in the next 10 years is cross-resolution, cross-band number remote sensing database model, and that's still really hard. Okay, are you using one specific model architecture? Yes, I have moved. We use Torch Vision because it's the most well-supported package. For example, YOLO, for those of you who haven't seen, had a massive security breach a month ago, and every time you installed the YOLO Ultralytics, I think it was version 10 model, it was also installing a crypto miner on your computer, so enjoy that. And so one of the reasons you have to create trust in this situation is there are real security risks. So we use the RetinaNet inside of Torch Vision. It is quite old, but at the same time, we find that data drives a lot of the performance. And so while you will get 2 to 5% in performance improves from transformers and more modern architectures like the DERTR from Detectron, for those of you who know that space, we often find that annotating data is so much more important than model selection that, frankly, you should spend time annotating more than you should be comparing models. And there's so much to do with downstream usage in terms of those confidence scores that 5% difference in accuracy is just not where we are right now in terms of needing to be that kind of fine difference. We need to understand how the model performs and be explicitly understanding its statistical properties, which I don't have time to talk about right now, but it's more important than doing a suite of models because you can get caught endlessly and there's thousands of architectures at the point. Our recommendation is choose an architecture that you trust and annotate your way towards success. Are Are there best practices in the extreme counts? I can't answer that question right now. That is too long of an answer. But class imbalance continues to be one of the dominant challenges. We undersample quite a bit, which is not satisfying, but is something we do. And so if you have too many high classes, we do cull at the top level. Frankly, class imbalance is still something we really need to work on. But I don't want to go too deeper into that. And I've decided that that is as much time as I'm going to do right now. Thanks, everybody. Please message me. We're happy to help you and hear from you about your use cases.